in this segment we're going to have a look at multipole moments of magnetic fields, and in developing multipole moments for magnetic fields we're going to follow very much the procedure that we followed for electrostatics. So I'd just like to remind you of how we dealt with multipoles in electrostatics. We started with the potential. Okay, so that's our standard expression for the potential, and then we made use of the following expansion. Okay, so we have this expansion for 1 on mod r minus r prime. The particular expansion that I've written here is valid in two situations. The first one is that r prime is less than r. So that is, we have some source distribution that I've drawn this way, and r prime here is clearly less than r, and we're interested in the potential distant from the source, where distant means we're many source length scales away. In addition, this expansion is valid when we have azimuthal symmetry. You'll notice we only have the Legendre polynomials here rather than the spherical harmonic. So azimuthal symmetry only, and those are the problems we'll be studying in this course. The angle gamma here is the angle between r, the vector r, the point of observation, and r prime. So if we substitute this expression into our expression for the potential, we generate the following expression. Okay, so we've simply done the substitution as I suggested on the previous page, and now we're going to restrict our attention to the lowest, the smallest two terms in this sum, the n equals 0 term, that is the monopole term, and the n equals 1 term. Okay, so there are those two lowest order terms. This one here you'll recognize as just our usual monopole term for the potential, and this is a contribution from the electric dipole that we studied earlier. You'll notice I've written an approximately equal sign here because I've chopped off the higher order terms in this expansion. So you might remember that once we had generated this, we recognized that we could rewrite the r prime cosine gamma term in the following way. Okay, and that was our expression for the dipole. So this is just the second term. This term here is just the second term. This one here, I'm not paying attention to this one at the moment. And this quantity here, we gave a name. This was the dipole moment, and we called that, we gave that a symbol vector p. So let's just finish off this development the following way. Okay, so this then was the expression that we developed for that second term in the expansion for the dipole. In magnetostatics, we're going to follow a very similar procedure, and we're going to start with the magnetic vector potential A. Now you'll notice that I've started with the one-dimensional form, the form where we have a line current. I could start with the expression for J, and if you look in the textbooks in more sophisticated treatments, they do indeed do that. but we're going to follow our textbook here and develop it using the one-dimensional treatment. We're going to use the same expression as we used in electrostatics for the expansion of 1 on mod r minus r prime. Okay, so let's just stop and comment on this. We've substituted this expression into here, and we've generated the first two terms. Again, I've not put in the higher order terms, we're not interested in them. You'll notice that this first term here, the lowest order term, in the case of magnetostatics, is 0. The reason being that we're integrating around a complete loop. I should have made that clear here. We're integrating around a complete current loop. It's a closed current loop. And so the integral of dl prime around any closed loop is going to be 0. You go all the way around the loop and come right back to the start. Okay, the second term that we've generated here, again, we can write the r prime cosine gamma part as r hat dot r prime. This is the same as in electrostatics. And we're going to use a vector identity. You can look it up and prove it if you like. We're going to rewrite this in terms of the area enclosed by the current loop. Okay, so we have replaced this integral with this form of the integral, and you can look that proof up if you wish. I'm not going to prove it here. It's not particularly instructive, so I won't bother doing that. Now we're going to, just as we identified an electric dipole moment, we're going to write this in terms of a quantity we call the magnetic dipole moment. I should emphasize this is the integral over the area enclosed by the current loop. So if we had a loop, for example, that looked like that, then the integral of dl prime, this dl prime that you see here, is this dl prime would be around here, and the dA prime that I've written here would be over the area. Alright, so that's the relationship between those two. Okay, so we're going to identify an object that we're going to call the magnetic dipole moment, and that quantity is going to be the following. And so we can now write the dipole term in the vector potential in the following way. Okay, so there is our expression for the magnetic vector dipole, the dipole term. In this case, the magnetic dipole moment given by this integral is located at position r prime, and we're interested in the value of the vector potential A at position r. So this is going to be an extremely useful, very useful expression when we come to consider magnetic materials.